All right, so in 5.2, we're going to continue the idea of discrete random variables that we started in 5.1 by talking about the mean and the standard deviation of discrete random variables. So two different concepts today, both in this video, and then we will have our homework assignment on 5.2 in Math Excel. So let's go ahead and get started with this. Boy, look at this. Let's just start with the definition of the mean. We've done the mean before. That's where we add up all the numbers and divide by the total. And so this is very similar to the population mean, only it's with discrete random variables instead of with an entire population, which could be any type of set of numbers. And so a lot of times we denote it as the mu, or the mu of x, which represents the mean. So whenever you see this symbol here, we're talking about the mean of the set of numbers, okay? And we have this formula. But man, how does that formula come about? And so let's really take a look at this down below, and we'll talk about how we come up with that formula. You can see it's the end result down here. So we're going to get to that towards the bottom of this slide. But a lot of times the mean would be the same thing as what the expected value would be. So if we're talking about a discrete random variable, which would be the number of siblings that somebody has, that would be whatever the mean is. If the average is 2, well then the average, the expected value, if we ask a new person, would be 2. Now it might be a little higher than that or a little bit lower than that, but on average the expectation would be 2. So let's say we have just a set of numbers. Maybe these are the ages of 8 different people. So we're doing a survey, maybe we're at the mall or whatever, we do a survey of whatever it is we're talking about, but one of the questions in the survey is we ask them how old they are. And so we have somebody that says they're 19, somebody else says they're 20, another 20-year-old, a 19-year-old, a 21-year-old, a 27-year-old, 20 and 21. So we know this formula from the past, that to find the average, we just take all of those numbers and add them together and divide by the number of numbers. That's what the n represents. Here we're having the sum of all of the individual numbers. So we could take 19 plus 20 plus 20 plus 19 plus 21 plus 27 plus 20 plus 21 divided by 8. We could simplify that process a little bit if we combined the same ages. Like for example, there are two 19-year-olds that were in the survey. Here we have two 19-year-olds. So let's just put those first. We have 19 and a 19-year-old. We have three 20-year-olds, okay, a 20-year-old, a 20-year-old, and another 20-year-old. So 20 plus 20 plus 20. Then we have a plus 21 and a 21-year-old. So two 21-year-olds and a 27-year-old divided by 8. These two things really are the exact same thing, just the numerator of these numbers are listed in a different order. Well, we could take this again and simplify it. Instead of, with our calculators, instead of going 19 plus 19, we could say, well, that's 19 times 2, because there are two 19-year-olds. Then there are three 20-year-olds. There are two 21-year-olds. And there's one 27-year-old. So we can add like the three 20-year-olds by taking 20 times 3 instead of taking 20 plus 20 plus 20. Well, this whole thing here can then be simplified to this whole thing here. So let's just see how. If I separate the denominator and put the denominator underneath each one of these parts, like I put an 8 underneath here and an 8 underneath here and an 8 underneath here and an 8 underneath here, have a common denominator, so I could still add them together, but that would mean that I have right here, I have two 8s. Okay, here I have 3 8s. Here I have 2 8s, and here I have 1 8. Well, that is what the probabilities are that are listed here. So in other words, we could take 19 times 2 8s plus 20 times 3 8s plus 21 times 2 8s plus 27 times 1 8. That's what we have listed here. But each one of these fractions is the actual probability for getting that age group. Okay, so the 2 8s, which we have here, is the same thing as 0.25, 25%. The 3 8s, which we have here, well, that's the same thing as 0.375. The probability of X equaling that specific age. And then we have the 2/8, which is the same as this probability, okay, or 0.25. And then we finally have our 1/8 over here that matches up with the probability of asking somebody their age and they're saying that they're 27 years old. That's 12.5%. So in other words, we can write what we have underlined over here, we can write it like this. Now this might look a lot more complicated, but it's how we get the final formula. We have 19 times the probability that they're a 19-year-old, plus 20 times the probability that they're a 20-year-old, plus 21 times the probability that they're a 21-year-old, plus 27 times the probability that they're a 27-year-old. All of that can be written in this formula. The sum of all of the ages times the probability that they're that age. So in other words, we could do the same thing by taking 19 times 0.25 plus 20 times 0.375 plus 21 times 0.25 plus 27 times 1.25, and then adding all those together to get the total probability. So that's what we would use to figure out the probability or the average of all of these numbers. We could do it, the simplest way would be this way, okay? But we want to use this formula, maybe not the formula, but at least the pattern on how to get the formula. Here's another example. Let's say we start with something like this. So it's kind of an interesting situation. A bank doesn't always have all the tellers there. Sometimes they might have 4 spots for tellers, but only 2 tellers are there because it might be a time of the day when there's not a need for all the tellers to be there. And so let's say we have Fifth Third Bank has 6 tellers available to serve customers every day at 1 o'clock, but maybe at 1 o'clock in the afternoon is not the time when most people are going to the bank. So they want to conduct a survey to see how many of those tellers are being used every day at 1 o'clock. And so they conduct a survey. Not a survey, but maybe they do a study, and every day at 1 o'clock somebody goes out and records how many tellers are actually being used. So for example, here we have 0 tellers being used, was 0.029 or 29% of the time. We had a teller that no tellers were busy. 4.9% of the time, 1 teller was busy. 7.8% of the time, 2 tellers were busy. 15.5% of the time, it was 3 tellers. 21.2% of the time, 4 of the 6 tellers were busy. 26% of the time, 5 tellers were busy, and 21% of the time, all 6 tellers excuse me, were busy at that time of the day. Well, if we use that formula, or at least the process, this is what we would do to figure out the average number of tellers, or the expected number of tellers every day. We could take the 0 times 0.29, which is 0. 1 times 0.049, which is 0.049. 2 times 0.078 is 0.156. And all I'm doing is multiplying things in this row by the things in this row to get everything in the third column. Okay? So I multiply all those together, and then I want to add them all together. So I add them up, and my answer is 4.118. Well, what does that tell us? What that tells us is that the mean, or the expected number of busy tellers on any given day at 1 o'clock is 4.118 tellers. Doesn't mean that every day there's going to be 4.118 tellers. It doesn't even really make sense about the 0.118. It's just the average. It's a little bit more than 4 tellers are busy at that time of the day every day. That's what the average here means. So here's what that means. If I just went out there on one day and I looked, I would expect to see 4.118 tellers there. But man, it could be 0 tellers, it could be 6 tellers, it could be 2 tellers. But in a large number of independent observations, if I go out there 10 days, the average of those 10 days is going to get closer and closer to 4.118. If I went out there 100 days, it would be even closer to 4.118. This is called the law of averages or the law of large numbers. Maybe it would be easier expressed like this. If I went out there on the very first day, maybe 5 tellers would be busy. Maybe the second day it would be 3 tellers or 2 tellers, and the average would be a little bit between 3 and 4. And I might be way off of 4.118 at the beginning. But the more times, the more days I go out there in a row and look at how many tellers are busy, the closer this is going to get to having 4.118 tellers busy each day. And both of those would be true. Even if I started out at 6, maybe twice in a row, eventually the average is going to come down to 4.118. So that's taking a look at the mean of discrete random variables. So let's take a look at a concept which is probably going to be a little bit more challenging for us, and that is the standard deviation of discrete random variables. So if you remember, when we did standard deviation, there was this formula, but we did most of it on our calculator. And so this is going to be harder to do on our calculator. What I'd like to do more of, and we'll get to this more in class, is how to do this with an Excel document. But we're going to use this formula. There's really 2 formulas that work, but we're going to focus on this formula to finding the standard deviation. And the standard deviation is the expected value. If we observe one day, on average, how close will that number be to what the actual average is? And so here's what really the process is going to be. We're going to take each x value, okay, that we have here and square it. So for example, 0 squared is 0. We have 1 squared is 1. 2 squared is 4. And that's how we're getting all of these x squared values. Okay, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. And we're going to take each of those x squared values and multiply it by the probability that the x is at that specific value. So here are all of those probabilities. If we multiply each of these probabilities in this column by the x squared, we get these numbers here. Okay, this is x squared times the probability that x is at that number. And if we add all of those together, we get 19.438. That's what this whole part of the formula here is saying. Okay, so if we have this, the sum of x squared times the probability that x is at that number, if we add all those numbers together, that's 19.438. Well, then we're going to subtract the mean squared. So we just figured out how to find the mean, which is to multiply each of these columns together, okay, and get those values and add them together. That's the mean squared. So it's going to be this number minus the mean squared. That would actually be considered the variance, but then we're going to take the square root of that number, which is 1.6. In class, hopefully we'll take some time to do this using an Excel document, so that we can see the process here, and we'll also do it by hand. But man, is it so much easier with an Excel document. But what that means is this. The standard deviation, what does that tell us? What does the 1.6 tell us about the different tellers at the bank? Well, it's going to tell us that each day, the average number of busy tellers at 1 o'clock will be 1.6 tellers away from the average of 4.1 tellers, or 4.118, depending on how we round. So that's what 5.2 is about, finding the mean and the standard deviation of discrete random variables. And we have an assignment in Math Excel that kind of hopefully will solidify this in our brains a little bit so that we can move on from here tomorrow. Do that assignment and we will see you tomorrow.